All to the Chairman's Seminar, both those of you in the audience as well as the people following in the webcast. My name is Alberto Ayala. I'm with the Research Division of the Air Resources Board, and it's a pleasure for me to welcome Chris Frey to Sacramento to give this seminar. Dr. Frey is a professor of environmental engineering at NC State. He's done a lot of very good emissions research work. His area of expertise is in risk assessment and exposure, and has looked at some modeling and the implementation of PEMS technology. So he's got a lot of great experience that I think is going to be very relevant and very useful to some of the work that a lot of us are working on here. And particularly the reason we wanted to invite Chris to Sacramento is because now he's looking at the climate angle of things as well. And obviously we're all very much involved and engaged in identification of potential mitigation strategies for climate emissions from transportation sector. So I think we're all very pleased to have Chris here. We appreciate his flying out here. He's running back to the airport because he's trying to make his first class tomorrow morning. So he's going to be on a red eye and try to make it to class. So we definitely appreciate your commitment to coming and sharing your good work with us. As usual, for those of you following the webcast, if you've got questions, we encourage you to send those questions via email. You can send the questions to sierrarm@calipa.ca.gov. And for those of you in the audience, if you'd like to ask a question from Dr. Frey, we please ask you to use the microphone so that the people following on the webcast can actually hear the question. So without further ado, please help me welcome Chris Frey.
Thank you. Good afternoon. I'm very pleased and honored to be here today as part of the Chair's Air Pollution Seminar Series. I know there have been a lot of excellent speakers for this event. And I'm going to talk a little bit today about identification and evaluation of potential best practices for greenhouse gas emission reductions in freight transportation. But I'm also going to take this as an opportunity to say a few words about where I'm coming from, which is North Carolina State University, which you may or may not be familiar with. It's a Research One university. It's part of the University of North Carolina system, which actually has 16 universities, including UNC Chapel Hill and NC State and others. Our university has 31,000 students and more than 2,000 faculty. And we, among universities that don't have a medical school, we actually have a fairly large amount of externally sponsored research, over 300 million per year. The university has 10 colleges, including engineering, agriculture, physical and mathematical sciences, veterinary medicine, and others. And NC State itself has a central campus in Raleigh, but also has facilities throughout the state of North Carolina. Since it's a land-grant university, it has a large extension service. I'm from the Department of Civil Construction and Environmental Engineering, which has about 40 faculty, about 900 undergraduate students, about 240 graduate students. I'm in the Environmental Engineering program, which has got about 12 faculty, and we cover environmental topics ranging from what I do, which is air pollution, to water wastewater treatment, solid waste management, groundwater, water resources, and coastal engineering. I'm going to talk about a specific area of research today, but I just wanted to mention that we're doing a lot of energy and environmental related research that I'm not going to go into detail on today. I might give some examples, however. As Alberto mentioned, I've done a lot of work on measurement and, here we go, measurement and modeling of the activity, fuel use, and emissions of on-road and non-road vehicles using portable emission measurement systems. I've done a lot of work on modeling and evaluation of advanced power generation and environmental control technologies. Of course, one area of current interest there would be mercury emissions. Another, of course, would be carbon capture and what to do with carbon coming out of fossil combustion systems. I've done a lot of work on quantifying uncertainty and emission inventories. We've been doing work on life cycle inventory and energy mix modeling of various energy systems, including looking at alternative fuels. I've done a lot of work in environmental exposure and risk assessment, and also various systems methods of dealing with variability, uncertainty, sensitivity analysis, and optimization in environmental problems. Just as an example of some of the field work that we do with portable emission measurement systems, and this will tie into some of what I'll talk about with the best practices for greenhouse gas emission reduction, is to instrument vehicles during actual operations in the real world to measure their activity, their fuel use, and their emissions. And this is an example where we are instrumenting a bulldozer, and we've tested several bulldozers and lots of other vehicles, with a portable emission measurement system that has gas analyzers and a light scattering particulate analyzer. It draws power from a battery. We instrument the engine to measure things like engine RPM, manifold absolute pressure, intake air temperature, and then that's used to calculate with the exhaust data the fuel and airflow through the engine. We have a GPS receiver to quantify the spatial activity. And so we've used this for a lot of different kinds of vehicles. We've developed a number of different methodologies for different kinds of vehicles over the last 8 years. And in recent work, we've been looking at biofuels, additives, comparing different engine certification tiers to see how effective they are in the real world, comparing different types of vehicles, and so on. Some other research related to that is we've done a lot of work on modeling of real-world vehicle emissions. For example, developing microscale and modal models of emissions to have high resolution in space and time of vehicle fuel use and emissions. And some of these other points I've already mentioned. Some other work that we're doing, and I'll show some examples of this in the presentation, is we're looking at auxiliary power units for long-haul sleeper cab freight trucks, and which is the first bullet here. We're doing a project that's sponsored by the US EPA, but it's in collaboration with Volvo, which has their technical center in Greensboro, North Carolina, to instrument and quantify the activity of a fleet of 20 in-use long-haul sleeper cab trucks to get an idea about the extended idling that occurs with these trucks during driver rest stops. And these trucks are all equipped with an auxiliary power unit system. And so we're quantifying the way the drivers use those systems. They use shore power. They use the engine for idling to supply hotel services to the cab of the truck. And so I'll mention that as one of the examples of what different practices might be that could reduce greenhouse gas emissions. We're also doing some work that I won't talk much about on the effect of land use on mobile source emissions, but this may be of interest to some of you. And as I mentioned, we're doing some life cycle inventory modeling to look at sort of the carbon intensity of alternative fuels and the overall emissions of the fuel cycle and the tailpipe emissions for particularly biodiesel, ethanol, and electric vehicles. We're also doing some work to support near roadway air quality studies, looking at how do you estimate emissions at very high temporal and spatial resolution, which is not really part of the capability of the typical emission factor models. Just very briefly, I'll mention another area we do a lot of work in, which is process simulation modeling of power generation systems. And this is an example called the Integrated Environmental Control Model. If you do a web search for that name, you'll find a website where you can download this model. This model is developed primarily at Carnegie Mellon University, where I did my graduate work. And since I've been at NC State, I've continued to contribute some of the components of this model, including the modeling, for example, of gas turbine systems. And so this has the capability to model a variety of gasification and combustion of fossil as well as some non-fossil fuels, and to look at gas cleanup, byproduct recovery, and some other things. Also in some other work, we've looked at byproduct recovery, co-production, say, of transportation fuels, and various kinds of comparisons. There's also a version of this particular model that deals with carbon capture, and that may be of some interest. This is another type of modeling environment for looking at advanced power generation systems based on gasification. This is a flow diagram of Aspen Plus chemical process simulation model that we use to quantify the performance, emissions, and cost of these types of systems. So we've done a lot of work looking at gasification-based technologies. And of course, gasification can be used with a variety of fuels ranging from coal, but also solid waste, heavy residual waste from refining, and other kinds of waste fuels. So it's a very flexible technique and probably more amenable to carbon capture than combustion systems. But having said all that, what I'm really going to focus on today is related to greenhouse gas emissions from freight transportation, looking at identifying, characterizing potential best practices. And I want to stress the word potential because I'm not going to repeat that word every time I talk about best practices. But what we've done here is essentially identify almost 60 potential best practices to reduce greenhouse gas emissions in freight transport. And we've done kind of a generic best estimate assessment of each one. Now, because I do a lot of uncertainty analysis and so on, you know, I'm fully aware that there's a lot of variability in how these practices would perform for particular, you know, vehicle owners or fleet owners. And so there would be site-specific issues that would need to be considered in a more detailed assessment. But one of the motivations for this work is that it did not appear that there was any systematic comparison or even listing of these best practices. And so I think some of the value of this is to have one compilation of these on at least a consistent basis. And as I'll talk about at the end, I think there's some ways this could be refined and improved to make it maybe more amenable to individual users who might want to make decisions at a vehicle level or a fleet level or maybe even a state government level. So one of the goals here is to quantify and compare the potential reductions in greenhouse gas emissions of different potential best practices, and also to develop a guidebook regarding these best practices. And where cost information was available, we tried to quantify cost as well as performance. There's not a lot of good cost data, and so we made a decision to only quantify cost where we thought there was some reasonable basis for doing that. Okay, so I'm going to talk about a lot of things. Some of them won't take a lot of time to discuss. So I'm going to define a few key concepts, talk about our overall methodology. I'll give a list of the best practices, and as you can imagine in an hour-long seminar, I'm not going to be able to go into detail on 59 individual best practices. So I apologize if I don't cover your favorite one in the talk, but there is a report available, and I'll give you the link for that toward the end with more detail. And I'd certainly be glad to have follow-up discussions with anyone who wants to contact me by email for more information. I'll talk about, on a modal basis, what the potential greenhouse emission reductions might be if these best practices are implemented, perhaps very aggressively, as an upper bound on what we might expect the benefit could be, recognizing that there are all kinds of realities, of the feasibility and logistics of implementing that would need to be considered in more detail in a second step beyond this assessment. We'll do some comparison of costs and cost effectiveness of various best practices. And a key point there is some of them will actually save money, and some of them might cost some money but provide a lot of benefit in terms of greenhouse gas reduction. So it's sort of a classic situation of, where would it make sense for a government to step in and provide incentives for things that the market otherwise wouldn't be adopting. I also talk a little bit about intermodal substitution. So, for example, what if you transport a ton of freight by truck versus rail versus water? And that has a significant effect on the greenhouse gas emissions associated with transport. And maybe we'll get into some of that discussion. And then I'll talk very briefly about the guidebook that's available online and some conclusions and recommendations. Okay, so kind of at the big picture level, if we look at greenhouse gas emissions in the U.S. In terms of tons of carbon dioxide equivalent, the U.S. is emitting on the order of about 8 billion tons of CO2 equivalent per year. And the freight transportation sector is just a little under 10% of that, so on the order of 700 or 800 million tons per year of CO2 equivalent. So it's a non-negligible part of the total, and in an absolute scale, it's a fairly large amount of greenhouse gas emissions. And then if we look at how that's distributed among different modes of freight transport, we identified and focused on 5 different modes. The trucking mode is almost 2/3 of that total of the freight-based greenhouse gas emissions. And I will say we're focusing here on the U.S., and we can get into some detail on, well, how do you deal with some of these emissions that are really based on international transport. But if you think of it as, we're looking at the U.S. component of any of this that's international in scope. So, for example, for water and air, we're looking at kind of an allocation to the U.S. of what is sort of the U.S. share of that. So the pipeline would be the second most important at about 16%, and then waterborne transport, shipping at 13%, and then rail and air roughly comparable, about 12% of the rest of the pie. If we look at what will happen, looking forward, and our baseline data was for 2003, which at the time was the most recent data that we had available. And looking at Energy Information Agency predictions about the increase in energy use and allocating that to the freight sector, if we assume that there's no particular effort to apply best practices to improve energy efficiency or reduce greenhouse gas emissions through energy use reductions, we might estimate, and this is basically just a scenario, but we might estimate about a 50% increase in the tons of CO2 equivalent emitted by the freight sector over that time period. And in both of these bar graphs, we show the distribution among trucking and then rail, air, water, and pipeline. So the trucking share, of course, will increase quite substantially, and then other modes will increase as well. But sort of the big piece of this is trucking, and then it looks like trucking would be responsible for the largest share of the increase that we might see in the next 15 or 20 years. And of course, that's an estimate. I mean, none of us knows what that's really going to look like. But, probably it's a reasonable enough assumption. So now we'll define some terms. We're going to talk about what we call best practices. And these could be technologies. It could be a more efficient engine, or it could be a different fuel, or it could be an operational strategy. Like it could be improved air traffic control or improved traffic management that would reduce energy use or greenhouse gas emissions. We looked at both existing or developing best practices. So some of them are commercialized. You could easily implement them. Some of them are concepts that haven't been proven. The focus, of course, is on reducing greenhouse gas emissions and what we're looking at. And for fossil fuel use, of course, that would be closely tied to reducing fuel use. When switching to alternative fuels that have less carbon intensity, then there may or may not be a total reduction in energy use, but the goal would be to have a total reduction in the greenhouse gas emissions. So those might go in different directions. Another component of this is to look at refrigerant use in the transportation freight sectors, and to look at either reducing leakage of refrigerants or substituting lower global warming potential refrigerants. And there's a slide I'll show a little bit later that gives some perspective on the relative importance of, say, the CO2 versus refrigerant. The other greenhouse gas that we looked at was methane. Okay. When we talk about best practices, it becomes evident that, say, for a particular freight mode, such as trucking, there might be multiple best practices that more or less serve the same objective. Like, let's say, for the example of long-haul trucks with sleeper cabs, during a rest stop, a driver would like to have either air conditioning or heating in the cab when they're resting. And they could obtain that service, let's say it's heating, they could obtain that service either from an auxiliary power unit, or they could obtain it from shore power, or they could obtain it from a direct-fired heater. And probably they're not going to install all three of those in the same truck. And so we grouped best practices into subgroups where there was either similar objectives or methods, and where there might be questions about best practices being mutually exclusive, where you wouldn't select all of them within a subgroup. And some other cases, there might be best practices that you could use simultaneously. And so we tried to distinguish that. Our focus on greenhouse gas emissions is on CO2, methane, and hydrofluorocarbons. These are the sort of the most, I guess, in terms of global warming potential, the largest emissions from freight transport. And the global warming potentials are indicated here on the slide. And as I mentioned, we're looking at potential best practices of different developmental status. And so, it's also useful to keep in mind some of them are easy to implement, some of them are, maybe concepts that need more development and demonstration before they're widely accepted. Okay, so what we tried to do then is identify potential best practices based on literature review and web review and talking to people, and then assess reasonable maximum reductions that might occur by 2025 in greenhouse gas emissions or energy or refrigerant use if these best practices are implemented, and then to assess the cost savings for these where data are available to support that analysis, and then to consistently report and compare these results. So I mentioned that there's a couple of analyses that we do for each best practice. Excuse me. One is looking at what is the potential benefit for an individual vehicle or the basic unit of application of a best practice. So for example, an auxiliary power unit would be applied to one truck. So what is the greenhouse gas emissions, per truck without the best practice, and then what are the emissions with the best practice, and then we can assess the per device reduction in fuel use and emissions. But then we also want to know to what fraction of the total modal activity is that best practice applicable. So for example, for auxiliary power units, this is applicable in the trucking mode, but not all trucks are long-haul sleeper cabs. So only a fraction of the total truck ton miles of freight is carried by sleeper cab trucks. So we want to figure out what fraction of the truck mode could be affected by this best practice. And then also we need to estimate, well, how much would these be used by, say, 2025? So how extensively would this particular technology penetrate to the on-road fleet? And then based on those estimates, we estimate a modal reduction in greenhouse gas emissions, which is basically the reduction per truck multiplied by the number of trucks to which we think this could apply by 2025. Now, for some best practices, let's say we're looking at the use of biofuel, the greenhouse gas reductions may not really be evident at the tailpipe of the vehicle, but they're evident in the fuel cycle. And so we did that analysis based on a life cycle inventory. Now, I mentioned that some best practices are perhaps could be applied simultaneously, and others are mutually exclusive. So where we had multiple best practices in a subgroup, let's say aerodynamic drag reduction is a subgroup, and there's many different ways to reduce aerodynamic drag, whether it's on a truck or an airplane. We might be able to do many of those things simultaneously. There isn't really a lot of data or any data to say, well, what's the effect when you do two or more of those things simultaneously? And so for now, we just made a linear combination of the effectiveness of each of them, recognizing that's probably not correct, but maybe it's an upper bound, and a more accurate assessment might consider interactions among them and maybe give a slightly lower estimate than what we're using. So this could clearly be an area where the estimates could be improved based on more focused work. In the case of mutually exclusive best practices, such as what I described earlier for shore power and direct heating and auxiliary power, probably wouldn't use them all simultaneously, or actually the worst case would be to use them all simultaneously, because you could actually increase total energy use and greenhouse gas emissions if one did that. So we picked one of them that had the highest potential reduction to represent that subgroup, and therefore we tried not to double count mutually exclusive ones. So let's say there were 5 alternatives within a subgroup. We would pick the one that offered the most emissions reduction and choose that. Okay, so this is just an illustration of the interaction effect if we had multiple best practices that could be used simultaneously. So let's say they could be used together. I'm trying to get the pointer here. So they could be used together, but they might interact. So what we don't really know is what's the interaction between the two best practices. As an initial guess, we assume we can just sum up their individual effectiveness to come up with a total effectiveness for, say, aerodynamic drag. Okay, so that could be a limitation, and that's something maybe that needs to be looked at more carefully. We have quantitative estimates of the energy use and emission reduction of all of the best practices that we identified. But what we don't necessarily have are good cost data for each best practice. So if we have cost data, then we did try to quantify the cost of these best practices and their cost effectiveness and their payback time, and we report that in a standardized table that includes cost. If we didn't have cost data, then we just reported performance estimates and what we refer to as a simplified summary table. And these are in the best practice document that you'll be able to get on the web. Okay, so we looked at a total of 59 best practices. And by the way, this work was developed in a draft form for the U.S. Department of Transportation, and they had an opportunity to go through 2 cycles of review, so we got some feedback from different parts of the U.S. DOT, such as the Federal Aviation Administration, on the air part of what we did, and so on. So this has gone through some review and comment. So, for example, for the truck mode, is where there seems to be the most interest and most activity, and of course the most fuel use and greenhouse gas emissions among freight transport. And this is just a list of the subgroups. These are not the individual best practices. So, for example, anti-idling, which I've mentioned, air conditioning system improvement to improve the efficiency or use different refrigerants, aerodynamic drag reduction I mentioned, tire rolling resistance improvement, hybrid propulsion, especially for local delivery or, say, refuse collection vehicles that have a lot of stop-and-go traffic or activity patterns, weight reduction, transmission improvement, engine improvement, reducing accessory load, providing incentives for drivers to use the vehicle more efficiently, alternative fuels. Those are the main categories we looked at, and then each of the categories we typically had multiple specific potential best practices. Then for rail, you'll see somewhat similar things to the trucking in terms of anti-idling, especially for switcher locomotives, weight reduction, rolling resistance improvement, alternative fuels, aerodynamic drag is obviously very important, but then things like air traffic management, weight reduction, improved engines, and then one might also consider the ground support aspect of air as part of the air freight transport emissions. And then water, things like propeller system improvement, anti-idling, alternative fuels, and pipeline. Some of the pipeline emissions are associated with control devices that use their pneumatic systems that use methane as a pressurized gas. And so process control device improvement is one way to reduce some of the bleed or leakage of methane. Methods for connecting to an existing pipeline to reduce emissions during the process of that connection, and then maintenance techniques. So there's a lot of different things here, and this may not, and probably is not comprehensive, but it's probably a good start in that it's identifying a lot of different things that at least seem to be discussed in the various freight communities. All right, so I'm going to just take one example and just to illustrate some of the issues with analyzing an individual potential best practice. So I'm just going to use the example of auxiliary power units. And this is an example of an anti-idling technique for long-haul sleeper cab diesel trucks. This particular auxiliary power unit, is a small generator, a small diesel engine with a generator that is packaged into a system mounted on the frame rail of a truck, and it provides electricity to run a heating and ventilating and air conditioning system located beneath where the driver would sleep in the sleeper cab of a long-haul truck. And the idea is that when the driver is resting for the hours of service regulation mandated, 8 to 10 hour rest period, that rather than run the base engine of the truck to provide power for heating or air conditioning, that they would run this much smaller diesel engine. And that engine might consume less fuel and therefore produce less greenhouse gas emissions. So that's the basic idea. Now, if one looks in the literature, goes to the Transportation Research Board annual meeting, and here's what people have to say about this, there's various assumptions that are often made about, well, what is the fuel use of the base engine when it's idling? A lot of people say it's around 0.85 to 1 gallon per hour. What's the usage for the APU when it's running? Some people say that's 0.2 gallons per hour. How many idle hours are there per year per truck? Some people say, well, there's 18,000 hours of extended idling during rest stops for a long-haul truck. And then how much does it cost to have this APU installed on the truck? Maybe about $8,000 to $10,000. How much does it cost to keep it running other than the fuel cost? Maybe about $500 per year. How long does it last? I think maybe we don't really know yet. What's the diesel fuel price? Well, when we did this analysis, it was about $2.56, which obviously is not what it is now. So then we look at, and this is just an example to illustrate, some of the detail of the estimates. We try to figure out, first of all, which is relatively easy to get at least estimates of, what are the annual ton miles for trucking. So there's about 2 trillion ton miles per year of freight in the U.S. carried by trucks. And then what we had to figure out is how much of that is in sleeper cab trucks. And there's not really data for that, so we had to estimate that. So we documented our estimate, how we came up with this, but the number we got was maybe it's about 450 billion ton miles per year in the U.S. by sleeper cab long-haul trucks. So if APUs were applied to some amount of market penetration on those trucks, maybe we might reduce 15 million tons of CO2 equivalent per year. And the associated energy use reduction might be about 185 trillion BTUs per year. On a unit basis, we might reduce about 66 times 10 to the minus 3 pounds of CO2 equivalent per ton mile of freight, and about 409 BTUs per ton mile of freight energy reduction. Okay, and then in terms of cost, these are some rough numbers for the cost. About $9,000 or $10,000 to buy it, $500 a year to operate. The annualized cost of owning and operating the APU is maybe about $3,000 per year. The energy savings might be a little more than that, so the net savings is about $440 per year. So why isn't everyone running out and doing this? And some of it is, well, maybe there's other issues that, maybe some truckers don't like APUs because they're noisy or they vibrate, or, well, that's nice, but this capital cost is pretty high. So even though there's a $440 savings, if we don't have money just sitting in a bank account, we're not going to just go out and spend this amount of capital to get that amount of net cost savings. So, the sort of implied discount rate for buying this unit may be very high for a typical fleet owner. There's some savings in terms of dollars per ton of CO2 emission reduction, and some net savings in terms of net energy reduction. And the simple payback period here would be about 3 years on this. So, maybe there needs to be some creative financing to give more incentive to use this. All right, now this is a slide you're probably not going to be able to read. I just wanted to illustrate in the report that there's a lot of detail on various best practices. So, for example, this subgroup here is anti-idling, and there's 5 different alternatives for that, of which auxiliary power units are just one alternative. And just to give you kind of an idea of what's on this slide, the numbers here are the percent reduction per truck in greenhouse gas emissions or in energy use. So for the APUs, it's about 10% reduction per truck. These are the percent reductions in greenhouse gas emissions and energy use for APUs applied relative to all of the truck emission reductions from all of the best practices for trucks. So the APUs might account for 2% of all the possible reductions that we might get from using all 33 best practices for the truck mode. And then the other numbers here I've already talked a little bit about. These are the magnitudes of the CO2 reduction and the fuel use reduction. Okay, however, that was based on some point estimates of what, people talk about. But if you look at the data more closely, in terms of fuel use rate of the base engine that's idling in a long-haul truck. Remember I mentioned that the sort of point estimate that's often used is about 0.85 gallons per hour. Well, Argonne National Lab uses 1 gallon per hour. There was a national survey of trucks that somehow came up with 1.7 gallons per hour, which I honestly don't think is an accurate number, at least apply to idling relevant to rest stops. And then there's some other data that imply numbers ranging from maybe as low as even 0.3 gallons per hour, which to me seems kind of low, to maybe 0.5. And so whether APUs are particularly effective at reducing energy use or emissions is going to depend a lot on what the energy use of the base engine is that you're trying to avoid. And that varies perhaps by engine model and by manufacturer and so on. All right, then what about the APU itself? And this is an estimate of the fuel use rate of APUs in gallons per hour for a whole bunch of different APUs, or for some of these are the same APU measured by different people. Some of these are vendor-reported numbers. Some of them are measured by independent testing organizations. You see one APU here that's got a very low fuel use rate of 0.05 gallons per hour. A lot of them seem to be around 0.2 gallons per hour. But what's not clear in a lot of these cases is whether this is loaded. Is this really producing enough electricity to power an air conditioner, or is this the APU idling without any load? Some of these tests were loaded, some of them were unloaded, some of them we don't know. So there's a lot of variability in these numbers too. So we've been doing a different project, not related to this greenhouse gas guidebook, but a separate activity to look at idle reduction technologies and to look at the activity pattern of freight trucks in the real world and how do they idle and what do they do when they're idling. And as part of this work, we're collaborating with Volvo, and Volvo has instrumented 20 trucks that they have sold to a couple of different customers about in the last 1 or 2 years. And we're going to just refer to one set of trucks as Fleet A. These are all owned by one fleet. The other is Fleet B, owned by a different fleet. And each fleet has 5 trucks with one type of APU and then 5 trucks with a second type of APU. We'll just call them A and B. So we have 4 strata of 2 different fleets and 2 different types of APUs. And these trucks are instrumented. Volvo already has the capability, as many truck companies do, to report electronic control unit data through a satellite-based system or a cell phone-based system. And that's often done for fleet owners to monitor what their drivers are doing or to track the maintenance of a truck. But in addition, there are a number of additional sensors that were installed to instrument the APU itself and to measure temperature inside and outside of the vehicle and so on. And there's an additional data logger that's connected into this satellite-based system for transmitting data. So we actually get every 6 hours, we get a report from each of these 20 trucks on, some of the data are reported every 15 minutes, but then they're stored and uploaded every 6 hours. So we have very detailed activity data for these trucks. So just as an example, let's say we were looking at the amount of idling that's reported by the electronic control unit. And here we'll include idling of the base engine plus the hours of APU usage. And we'll say that for a given truck represents the total amount of idling. And we have here examples for 2 different trucks. So for truck 1, that totaled about 1,800 hours per year. That's kind of like that estimate I talked about a little while ago. For truck 2, it's about 2,200 hours per year of just total reported idling. However, some of that idling occurs over short periods of time just in traffic. So if we exclude the idling that was less than 15 minutes, and we'll call 15 minutes or more, just for lack of better terms, this we'll call long duration idling. Well, that's only about maybe 1,200 or 1,300 hours for truck 1, not 1,800 hours. And likewise, truck 2's long duration idling is about 26% less than the total reported idling. And then if, let's say we just pick a criteria, let's say we want to know how much idling had a duration of 6 hours or more. Well, that's only about 800 hours for truck 1 and maybe 1,400 hours for truck 2. So it's probably not the case that there's 1,800 hours per year per truck of rest stop idling, and rest stops should actually be longer than 6 hours. One thing we're also seeing is, drivers may or may not be taking the full 10-hour rest stop, but that's another issue to talk about maybe in a different forum. But the main point is that if you really focus on extended idling that might be representative of rest stops, it's not nearly as large as the 1,800 hours. So, if you look at the site-specific data, which didn't really exist or is only becoming available more recently, then you get a different picture of APU engines. And so my point is not so much to either advocate or disadvocate for this particular technology, but just to say that, it's one thing to use generic point estimates. It's another thing to get more into the site-specific information as to whether this makes sense for a specific vehicle owner. So, it may make less sense for some of these vehicles than it would for someone who's doing a lot more extended idling, or if they have a very inefficient base engine, or they're able to use a very efficient APU. This is some work that we've done to measure the fuel use and emissions of the base engine of a truck and the APU engines. And for the particular truck we looked at, its fuel use rate was only about, say, 0.5 to 0.6 gallons per hour, depending on ambient temperature, which is a surrogate for whether it's using air conditioning or heating. And we did some measurements to quantify the emission rate of different pollutants, including CO2, at different rates of fuel use. So this is gram per hour NOx emissions, kilogram per hour CO2 emissions. And then for the two different APU engines, and one thing you might notice is the APU engines at high load might consume as much fuel as the base engine does at low load. So the differential in fuel consumption might be on the order of 1/10 of a gallon per hour, maybe a little more than that. In some cases, maybe it could be a little higher than that in other cases. So here there's some modest fuel use benefits. We just highlighted a couple of columns to illustrate, there are substantial reductions in the NOx emissions for the small APU engine compared to the base engine, and also in the CO2, of course, proportional to the fuel use. And, one can get into all the other pollutants, but in the interest of time, I won't go into a lot more detail on this. But what we're doing in this project is trying to quantify for each individual truck the amount of fuel saved that's avoided by using the APU instead of the base engine. This is gallons of fuel saved. And this is highly variable among different trucks. The amount of avoided NO emissions, hydrocarbon emissions. So a positive number here means the APU has lower emissions than the base engine. The CO emissions might be going up, but also the CO emissions are fairly low for either engine. Some of this may have to do more with detection limit issues than real differences. The avoided CO2 emissions for some engines or some trucks are fairly substantial. Some are very low because they're not using the APU very much. And then also some avoided PM emissions. So just comparing these trucks, some of the trucks are operated by an individual driver. Some are operated by two drivers who rotate. So one driver could be resting while the other one is driving. So these team driver trucks tend to use the APU or extended idling much less than the single driver truck. So that's another factor. And even for a given truck, some drivers don't like the APU. They won't use it, or they use it very little. Other drivers will use it much more, as we see in comparing these different fleets. So some of it's behavioral. Why is it some drivers don't like the APU? Why won't they use it more? Or should there be incentives to get them to use it more? Okay. So that's just to give a little bit of flavor of, let's see, I think I'm going in the wrong direction here. Okay, I don't know what I did there. Somehow I switched this so it only goes backwards. All right. Let's go forwards. Okay, here we go. All right, so anyway, so the main point is, there's a lot of detail here, but the main point is site-specific variability could be quite important in an individual owner's decision to adopt a technology such as this. So the actual fuel savings, emission reduction, and so on can be highly variable. So the results here in our best practice study are meant to be kind of typical numbers, but they're not necessarily site-specific values. And so therefore we think, a next step in this work would be to develop a tool to identify, compare, and evaluate best practices using data relevant to an individual decision maker who's interested in adopting these best practices. And their decision might not be the same as someone else's decision because they have different situations. Okay, I'll talk about another example looking at life cycle inventory and real-world tailpipe emissions for soy-based B20 versus petroleum diesel. And of course, here we have to look at the life cycle to understand the carbon intensity of the fuels. And there's also some geospatial implications of using biofuel that I'll mention. And then the real-world implications for tailpipe emissions. And we've done some in-use measurement of 35 different diesel engines on different types of vehicles, including both on-road and non-road vehicles. I guess before I move on to the next slide, for those of you who have looked into B20 biodiesel, for example, there's a fairly well-known report by the US EPA based on summarizing engine dynamometer data that indicates that you'll have 10 to 20% reductions in pollutants such as CO2, hydrocarbon, and particulate matter, but you might see a little bit of an increase in NOx emissions, and maybe 2%. And a lot of policymakers and fleet owners and so on have looked at that increase in NOx emissions, and they're in a non-attainment area for the National Ambient Air Quality Standard for ozone, and they're thinking, well, we just can't do that. And so there's been some hesitance to use biofuel for that reason. And there are some other reasons as well, but that's one of them. So we've done some in-use measurement to try to understand what's happening in the real world, and I'll talk a little bit about that. So for the life cycle, we need to have a system boundary for the petroleum diesel life cycle to quantify, what are the CO2 emissions and other emissions associated with producing diesel fuel from crude oil recovery through delivery, to the vehicle, and then also for the biodiesel life cycle. And some of the main differences are that, of course, we have farming, we have a soybean oil plant, then there's some transport to a biodiesel plant for further processing, and then there's transport to the vehicle where it's used at the end. And in the analysis I'll give you some numbers for, we're more or less assuming that there's an existing soybean farm, that we're not clearing a forest to create a new farm. And if you were to, say, deforest to create new farmland, then that would affect the CO2 intensity of this alternative fuel. All right, so under those assumptions, if we look at the energy, for example, the energy associated with fossil fuel and renewable fuel to make petroleum diesel, there's very little biofuel because right now we don't use a lot of biodiesel in the U.S. So there's a little bit of biodiesel that might be used to transport, and so there's a very tiny amount. So let's say petroleum diesel is essentially all fossil fuel, and so you have a lot of CO2 emissions as a result. B20, there's an increase in the total amount of energy to produce a gallon of B20, but only 83% of that is fossil-based, and the reduction in the fossil energy use compared to petroleum diesel is about 9%. Now that could be specific on specific situations of that life cycle. And even B100, under the current energy mix in the U.S., there's a lot of fossil transportation fuel that would be used to deliver this fuel. So maybe there's about a 45% reduction in the fossil intensity of B100 compared to petroleum diesel. Now, if we went to an energy mix that was more heavily biofuel-oriented, then these percentages could increase. And on the other hand, if we were clearing forested land to do farming to create these biofuels, these percentages could go down. All right, now this is a fairly complicated assessment. I haven't given you all the background on this, but basically, just to give you an idea of, we've done some different scenario analyses, and let me focus on NOx as an example, where we looked at the fuel cycle emissions and also the tailpipe emissions associated with making petroleum diesel. And of course, the tailpipe emissions are quite dominant if you're using petroleum fuel, but there are some NOx emissions associated with producing the fuel. And then this is an uncertainty range in the total emission estimate for this life cycle. if we make a soy-based biofuel with a new soy oil plant that is compliant with the most recent new source performance standard that applies to that kind of stationary source, but if we assume EPA's dynamometer data as the basis for the emission factors, we would estimate a slight increase in both the tailpipe NOx emissions and the total NOx emissions. However, if we use some in-use emission factors, which I'll talk about in a minute, that indicate perhaps a slight reduction in NOx tailpipe emissions, then there might be a slight net increase in NOx emissions. So if we look at some other fuels, some other pollutants here for VOC, we would expect that for a new soy oil plant, maybe there's not much net change in the total life cycle emissions. If we use an old soy oil plant, which tends to have higher VOC emissions, then we would have an increase. So in terms of the benefits or disbenefits for other pollutants, it kind of depends on what technology is used for the processing of the soy fuel-based fuel, and then what are the real-world emissions of these. For CO, it looks like there's a slight net reduction in life cycle emissions, as seems to be the case for particulate matter. Okay, but then there's a question about, well, where is this going to happen? If we look at, for example, locations where there are biodiesel plants, which are these circles, the dark circles here are biodiesel plants that are located in ozone non-attainment areas, and then the stars are biodiesel plants located elsewhere, typically in rural areas. And then the green are the ozone non-attainment areas as of when we made this graph, so it's not exactly the same as if you look at EPA's latest map. And then this is where soybeans are made. And a lot of the soy oil plants are going to be located fairly close to soy farms. And so you'll have the soy oil biofuel processing plant, usually within about 75 miles of a farm, and then that fuel might get transported to some relatively local market. So there's a question of, if we're using biofuel in a non-attainment area, are we going to have lower NOx emissions as well as lower CO, hydrocarbon, PM emissions? And then if we're producing the biofuel in a non-attainment area, then the whole life cycle might be occurring in that same location, and that could change the comparison in some cases to whether you have higher or lower emissions. Or you might have a situation where you have benefits of lower tailpipe emissions in a non-attainment area, but you have maybe some disbenefits of higher emissions for the fuel cycle occurring in a rural area. All right, so another aspect of this is to try to understand what are the emissions in the real world for these vehicles, and we've done some measurements of different kinds of vehicles, for example, dump trucks. And we've done an in-use measurement of 12 different dump trucks that represent different chassis sizes and different engine certification tiers. So we have single rear axle dump trucks, which weigh about 33,000 pounds gross vehicle weight, and then double rear axle, or what are called tandem dump trucks, at about 50,000 pounds gross vehicle weight. And this is a study we did for the North Carolina DOT, where we measured these vehicles as they were operating throughout Wake County in North Carolina, which is where these particular vehicles were stationed. And we've given presentations on this before, so I'm not going to go into detail on how we got these results, but I can point you to more detail if you're interested in. Kind of the bottom line is, if we look at an average over unloaded and loaded operation of these dump trucks, we saw these are the percentage changes in fuel use and emissions. And I will say that the 7% increase in fuel use is slightly influenced by one vehicle that was a little strange because it was towing a trailer during one of the tests. So if we exclude that vehicle, the percentage change in fuel use was a little bit less than this, more like 1 or 2%, which is what we would expect given the properties of biofuel versus petroleum diesel. But what we found was there was about a 10% reduction in nitric oxide emissions, which constitute about 95% of the total NOx emissions from diesel engines. And comparing that to the engine dynamometer database that EPA put together, from which they estimate a 2% increase, that's quite a difference. On the other hand, the percentage changes that we observed in hydrocarbon, CO, and PM emission rates were very similar to the percentage differences based on EPA's database. And then there's a slight increase in the total CO2 emission rate because of the ratio of carbon to energy content of the biofuel. But there's still a net reduction in the fossil content of that carbon based on whether we're using an existing farm to produce the bio stock for making the fuel. So then there's a question, well, why would there be a reduction in NOx emissions, and is that even a real thing? Maybe this is some artifact. And so we've also done some measurements on some cement mixers, and this is the average of 8 different vehicle tests. Here we saw a small decrease in NOx emissions, and actually more substantial reductions in emissions of some other pollutants. And then we've also done some testing on non-road vehicles, and I won't go through all the procedure that's shown here, but we've tested backhoes, front-end loaders, and motor graders and looked at the percentage change in NOx emissions as well as PM, hydrocarbon, and CO. And the average over 15 vehicles was a slight decrease in the NOx emissions and also substantial reductions in emissions of other pollutants. So, biofuel may offer some advantages in terms of reducing carbon intensity, but then, sort of one of the potential showstoppers has been what's it going to do to NOx emissions. And looking over all of the 35 engines we've tested, it seems like there's, on average, a reduction in the NOx emissions, not an increase. Now, why is that? Well, one reason may be, and this is not just our opinion, but some others are also of, I think, this opinion, that if the biofuel is made from a B100 blend stock that's compliant with the ASTM standard for B100, that seems to be associated with situations where we're seeing these kinds of reductions. So all of the tests we've done are with fuels that, as we understand, meet that standard for the B100 blend stock. There have been some other tests with fuels that the tester knew did not meet that standard where the NOx emissions have been higher. So the fuel quality may be one key issue. Another issue could be that we're looking at real-world duty cycles and not a standardized engine dynamometer test schedule. Okay, so again, you could go into a lot of detail on any of these best practices. So I've kind of picked 2 examples to go into detail on. But let me come back to the big picture of looking at, all right, well, suppose we use all of these 59 best practices, and what might the benefit be? And is that benefit substantially large, or potential benefit substantially large, that we ought to look at this more? So here's an estimate of the reduction in the total modal greenhouse gas emissions as a percentage. So for example, this 57% means this is the total reduction in 2025 in greenhouse gas emissions for trucks compared to what might happen in 2025 if we don't implement these best practices. So this is assuming you implement all of the best practices, all 33 for the trucks, and they all perform as advertised. And some of these are commercially available. That might get you about 25% reduction. So, if you're kind of risk averse and you only want to look at commercially available systems, well, maybe there's only a 25% reduction. If you're a little more aggressive and, things that have had some pilot testing, you want to include that. That gets you up to about 35% reduction. And then if you add in some new concepts that aren't really fully proven yet, that gets you up to about 57%. For rail, maybe about a 20% overall reduction. For air, maybe 35%. For water, maybe 5%, and same for pipeline. Okay. So now this is based on fairly aggressive implementation, and your mileage may vary, or it may not perform quite so well as what's shown here. So this is probably a bounding estimate on what the potential could be. If we look at the same information, and I'm sorry somehow it cut off the legend here, but this is the same percentage reduction in 2025 with and without the best practices. If we look at the allocation among greenhouse gases that we considered, for the truck mode, it's mostly CO2 related to energy use reductions or alternative fuels, and a very small amount related to reducing refrigerant leakage or substituting lower global warming potential refrigerants. For rail, air, and water, it's really all based on CO2. And then for the pipeline, it's really all based on reducing methane discharges from the pipeline system. Now, this is a similar perspective looking at 2025 with and without the best practices, but looking at the magnitude of the reduction in million tons of CO2 per year. So, for example, for trucks, for commercially available systems, maybe we might see 175 million tons of CO2 equivalent reduction with that set of best practices. Then if you could implement the pilot test, that gets you over 250. And if on top of that you implement new concepts, that gets you over 400. So that's a fairly substantial reduction. And then the magnitude of reductions from these other modes is quite a bit less. Rail, air, water, pipeline. In part because these contribute less to the total freight greenhouse gas emissions, and in part because the percentage reductions estimated for these are smaller than for the truck mode. Now, this is a different perspective on the trend over time. So what I just showed before was only looking at 2025 with and without best practices. This is comparing 2025 with best practices to 2003, which is our baseline year. Just to get an idea, if you remember early in the presentation, I showed a slide implying energy use might increase 50% for freight transport from 2003 to 2025. And roughly speaking, that might mean about a 50% increase in greenhouse gas emissions, plus or minus. If we were to aggressively, implement best practices in the truck mode, maybe there might actually be a reduction in greenhouse gas emissions, even with the growth and activity that's projected for freight in 2025. So perhaps a 30% reduction. For some of the other modes, basically all the other modes, there would still be slight increases in greenhouse gas emissions, assuming the growth and activity for those modes and using best practices. So what the best practices would do in these cases is just reduce the amount of increase in the greenhouse gas emissions for those modes. So if we wanted to see reductions in these modes, maybe something more substantial has to happen. And overall, maybe about a 10% reduction in greenhouse gas emissions, coincident with the 50% increase in energy use. Now, again, this may be sort of an optimistic bound on what might happen. Okay, now we did look at the cost of some of these technologies. There were only 13 of them where we thought we could get good cost data. And so we have 5 for the truck mode, including various anti-idling techniques, hybrid trucks, and biodiesel. And then for rail, we had basically anti-idling types of techniques, hybrid switching locomotives, plug-in systems for anti-idling, and biodiesel. And then biodiesel for marine applications, and then various systems aimed at reducing leakage of methane from pipelines. So I'll just focus on the truck modes as examples. So this is displaying, if I can get the pointer back, here it is, the greenhouse gas emission reductions in million tons of CO2 equivalent per year that might be attributed to these individual potential best practices. And if we look at kind of the 2 big ones here, it's the hybrid trucks, which might provide benefit in stop and go types of duty cycles, and then the B20 biodiesel, which could provide possibly benefits for any truck. So those might offer the largest individual magnitudes of emission reductions. And then if we look at the net cost savings, and I'll just focus on those 2 again, hybrid trucks will cost more money, of course, but they will use less fuel. And depending on the fuel cost, you might actually have a substantial savings. And by the way, this is just an anecdote, nothing to do with freight, but I was in San Antonio about a month ago, and a lot of the taxis are hybrids. And I was talking to the taxi driver about, because we were in a hybrid Camry, and he was saying, he saves a tremendous amount of money in fuel. So for him, the payback period on buying a hybrid is very short. So where you have very high mileage vehicles, there might be tremendous benefits from that. But again, with any new technology, a user wants to make sure it's going to last before they're going to spend money to adopt it. The B20 biodiesel, although it had that large reduction in emissions potentially, there's a fuel cost premium for this, at least now. So it costs more money. And so if a fleet owner is going to use it, maybe a state government might use it, like North Carolina, where they're using it to comply with the Energy Policy Act. But a private owner, why would they use it? Maybe they use it because they want to be a good citizen, but it's going to cost them more money. So what's the incentive? Okay, another perspective, and this is, I think, an interesting comparison, and it's obviously a very simplified comparison, and hopefully not. I don't want to present it in an overly naive way, but if we look at the intensity of greenhouse gas emissions among different freight transportation modes, and we compare, this is pounds of CO2 equivalent per ton mile, and we compare truck, rail, air, water, pipeline. Well, air, we're not surprised that air is the most energy intensive per ton of freight transported per mile of transport. But, generally, if we're using air, it's, to send a FedEx package somewhere. It's not that we're going to transport a gas turbine engine through an airplane to a customer. So, there's a certain market niche for air freight that maybe is not comparable to some of these other markets. But probably the ones that might tend to capture your attention would be truck versus rail, or truck versus water if you're living near the Mississippi River, for example, or in a coastal area. And, this suggests that, well, if we could encourage where it makes sense for a ton of freight to be, transported by rail instead of truck, or by water instead of truck, that would have huge benefits, larger than any of the benefits we've been talking about for implementing a best practice within a particular mode. But then, of course, there's a lot of reasons why, trucks are used to transport freight and for some kinds of freight, and rail's used for other kinds of freight, and, maybe they don't mix and match so well. So, there might be an opportunity, for example, hypothetically, if you could move a ton of freight off a truck, and at least for most of the trip, put it on a train, even accounting for, the beginning of the trip might be on a truck, and the end of the trip might be on a truck, maybe you could get a greenhouse gas emission reduction on the order of 85% per ton mile of freight transport. But, the actual reductions would depend on site logistics, and, so I wouldn't expect that you could get an 85% reduction overall, and maybe it's only 1% or 2 or 3%. So I think this is an area where it'd be interesting to do some more work to understand what that potential benefit could be. So in terms of our guidebook, it's available on my website, which has kind of a weird URL. So it's www.ncsu.edu/tilde, and I have a link to this report on my homepage. The report has background and methodology in chapters 2 and 3, and then we go through fuel properties and an appendix. And then we have a series of chapters on each of the different modes that gives kind of the bottom line results and a little bit of description of each best practice. And then we have supporting appendices that give the details of all the assumptions and estimates that we made where there wasn't data that we could directly look up. And then there's summaries of and comparisons between modes in Chapter 9, and then conclusions and recommendations in Chapter 10. So there's a lot more detail in that report. It's a several hundred-page report. Okay, so in terms of conclusions, well, there could be lots of different conclusions. One might be, well, if you could aggressively implement best practices, then you might see a net decrease in total greenhouse gas emissions in freight transport. And I'm sure if you're a government agency, that's exciting. If you're at a shipping company looking at this on the web, you're probably really nervous about this statement. So again, this might be a sort of upper bound benefit that might accrue. And I think there's a need for more detailed analysis to better quantify this more accurately, or to look at it on a more site-specific basis. I'm sorry, let me go back. And then even larger percent reductions might be possible per ton mile if you could shift between modes. So how do you encourage that? How could you create incentives for that, and how effective would that be? Okay, some other conclusions. Right now, it's really difficult to assess the cost of a lot of these. There just isn't really good data, and that would be another area where there could be more information collected more systematically than we were able to do with the resources we had. But where we did have cost data, it's clear that there's a lot of variability in kind of the cost effectiveness and the payback period of different technologies. And a lot of the cost savings depends on the magnitude of energy reduction. But even in cases where there's a net savings, that net savings by itself may not be enough incentive for people to adopt these best practices. So, there needs to be some effort to figure out how to promote the diffusion of these. And some of it is demonstrating, especially the pilot and commercial scale techniques, so that in the commercial marketplace they're viewed as proven technologies. And some of it may be dealing with sort of nuisance issues with some of these, things like the vibration I mentioned with an APU, may be an issue for some people. Okay, so then, some best practices may offer potential for large reductions in greenhouse gas emissions, but maybe they're not cost effective. So these might be the ones that you really would like to promote, but no one's going to adopt them unless, there's an economic incentive to do it, or I guess unless they're told to do it. Maybe there are ways to reduce the cost of these alternative fuels to make them more attractive, for example. So, from a national policy perspective, this might be a classic case where a government should promote some research and development and demonstration to promote, the greater good of reducing national greenhouse gas or state greenhouse gas emissions. So it's clear that, some best practices potentially could lead to some no regrets outcomes. There's net savings to the operator. There's reduced greenhouse gas emissions. Maybe some of it's just a need for more education and dissemination of information and networking to convince people that, they'll do well with these. And others, as I say, may have to overcome some perceived or real nuisance type issues or some cost issues. Okay, in terms of, other related work, I've mentioned that we've been doing a lot of work looking at B20 versus petroleum diesel. We're also doing some work looking at a plug-in diesel hybrid school bus. There's about 19 of these prototype hybrid school buses around the country, and one of them is in Wake County where we're located. So we've done some measurement. We don't yet have the results yet to present, but we're currently analyzing data from this bus. So, there's some other hybrid utility vehicles that are being used by Progress Energy and some of the electric utilities that are, really now getting into promoting plug-in hybrid vehicles. And, I'm hoping we might have an opportunity to do some measurements on those types of vehicles. We're also planning to do some testing on passenger locomotives. The state of North Carolina operates a train from Raleigh to Charlotte, and they're interested in switching to biodiesel and also retrofitting with some emission reduction technologies. I think another area of, I've mentioned some of these other areas already, so I won't go into detail. We're also doing some international collaborations. This is a photograph of, you probably can't see this, but this is a Honda. It's a Guangzhou Honda. It's made in Guangzhou, China. So this is a Chinese license plate. You think about greenhouse gases and, how many of these Hondas and Toyotas and Buicks and so on are being used in China. And so if we're, CO2 doesn't really care whether it came from China or California or North Carolina. So, we may want to engage in trying to figure out how to assist in promoting technologies for use in other countries to try to mitigate greenhouse gas emissions. So in terms of some recommendations, I think, this best practice document that we've developed, it's probably out of date as soon as it's published. It's the kind of thing where you kind of have to continually update it as new information becomes available, revise and develop cost estimates as new data become available, further evaluate the key assumptions that influence the selection of best practices through a more extensive sensitivity or uncertainty analysis. And we also think it would be nice to develop a computer-based decision tool like a decision tree or a decision support framework that an individual user could put in their own site-specific data, like here's my fuel cost, here's what I think it costs to get these technologies, And then it could rank all of these best practices for that individual user, and that ranking might be different than for a different user. So, I mean, that's something we'd certainly be interested in working on if we had resources to do that. So I should mention this work's been supported by a lot of different sponsors, none of whom are responsible for what I've said here today. And I also want to acknowledge a number of my students. Po Yao Kuo actually did a lot of this greenhouse gas best practice guidance document work. And Kang-Woo Kim and Shi-Hao Pong have done a lot of the in-use measurement work. Haibo Zhai is doing a lot of microscale emission modeling work. And Phil Lewis is a PhD student also who's done a lot of in-use measurement. William Rasdorf is a faculty colleague, who's done a lot of construction vehicle work with me. And Charles Villa is with Volvo, who's done a lot of the instrumentation of the in-use fleet of long-haul trucks. So if you have any questions, if we don't have time to cover them all today, here's my contact information. You're welcome to email me or give me a phone call. And I think with that, I'm not sure where we are on time, so I'll turn it back over to I guess, Alberto, if you want to moderate, or if you want me to moderate, or whatever the procedure is. I'll be glad to take questions.
We'll go ahead and take questions now. We've got a handful of them from the webcast, so
Okay, good.
we'll do one-on-one. So, in the audience?
Yeah, I guess I have more of a comment than a question. I agree with what you were talking about in terms of mode shifts and the potential for greenhouse gas benefits on that. One comment I have is that with regards to your ship and water movements, that it looked like you didn't have a significant growth rate in ships, but what we're seeing on the West Coast is a significant increase in shipping emissions that's due to larger ships coming into, say, the ports of Los Angeles and Long Beach as freight moves from Asia into California's ports and then out across the nation. And I know that IPCC guidance doesn't necessarily focus on international shipping. It looks at domestic, but we think that that's something important to look at. One thing I did notice on one of your charts was that you had ship transport being less efficient than rail transport, and I wondered if that was an artifact of focusing mostly on domestic shipping, or if you could comment on that. And then finally, I would say that in terms of operational efficiencies, it seems to me that it's important to understand that because fuel costs have been low for the past 15 years, things like just-in-time delivery systems that have sort of matured over that period may have been economically efficient but not fuel efficient. And so there's probably room at looking for the way industries operate, like the trucking industry, to better understand how they're operating and how those things might be tweaked or changed in terms of incentives to get better fuel economy and benefits from that perspective. And one example of that is like port drayage operations. We've done a drayage truck emissions inventory looking at them, and there's a large fraction of trips in DMT that are associated with truck repositioning, where a truck basically moves from one destination to another where it's pulling nothing but burning fuel, and it's doing that because they either don't have an empty container to return the port, or they end up at a destination delivering a container where they don't have anything to bring back. So those types of ways of increasing efficiency, I think, could provide some benefits. But perhaps you could comment on the ship versus rail fuel efficiency.
Okay.
Where the data come from?
Well, yeah, I guess even your first comment about the growth rate in different modes. So, these numbers are sort of national estimates, and when you apply them in a specific area, I think part of my point was this is sort of a best estimate at sort of a national scale. And so if you apply them locally, it may not be that representative. So I think that's part of, where I'd like to see the next step of making this into more of a user-specific tool where you can do these assessments at more of a local scale. Yeah, I think on the ship emissions, we did some estimates where we, sort of allocated emissions within the U.S., and, you may be right that it may have something to do with that. I can't give you an exact answer right now. I'd have to kind of look at that. But, that could be a reason for that.
Okay, thank you. Let me, Chris, let me give you one from the webcast. Let's see, somebody's working on a voluntary carbon credit market protocol for quantifying greenhouse gas emission reductions associated with using anti-idling technologies for freight trucks. And the question has to do with the APU running as well as the engine idling. Is it possible that truckers could use an APU or electrical plug-in at the same time that they idle their engines because the unit cannot provide enough power for all the heating and electricity needs? And if so, is there any data available regarding how frequently this happens?
Yeah, that's a good question. And the answer is, I think the answer is yes. And we have seen a little bit of that in our data. And there will be data on the frequency of that. We haven't kind of finished analyzing that yet. So that's one of the things we expect to report on. So I think I alluded to that a little bit, that, some of these anti-idling technologies, potentially they could be used together, which is kind of defeating the purpose of using them in the first place. So if you were to run the APU engine and the base engine at the same time, then, you've increased your fuel use. One thing that, we did sort of a parking lot demo with one of these, and one of the things is if you're going into a truck that's been sitting out in the sun and you want to cool it down really quickly, one thing you might do is run everything to really pull the temperature down quickly, and as opposed to just running the APU or just running the base engine, from sort of a behavioral perspective. Now, obviously that's not optimal from an energy perspective. So maybe there can be a technological fix where there's some kind of interlock between the two, and they're not allowed to use them both. Maybe that might be necessary. So there may be a behavioral issue there, and maybe there's a technological way to try to avoid that. But I think it's fairly infrequent, is what we've observed. It does happen sometimes, but it's fairly infrequent.
Chris, thanks very much for the interesting talk and the bonus information on PEMs and biodiesel. I wanted to talk a little bit about the air quality linkage.
Okay.
So it's well established now that diesel soot has radiative forcing, and so would be part of the climate footprint of a lot of these sources you're representing. And even though the science is still emerging on quantification of this radiative forcing, it's maybe something you could include in the next generation.
Yeah, that's a good point.
And then also some of the measures that you've described, like anti-idling, will have public health benefits and reduce pollution, and maybe those co-benefits could be quantified in the next version as well. Yeah.
Okay. I'll give you another one from the webcast. The gentleman is concerned that we will be shrinking car sizes to get better mileage. Meanwhile, the trucks keep getting bigger. Already competing for space on freeways with these big rigs is a problem, let alone the damage they cause on the roadbed and especially feeder roads. I guess he's interested in your commentary. Isn't it about time to shrink the size of trucks? And has anybody done any comparison to look at the benefits, fuel consumption between the big rigs and potentially redesign smaller trucks? The main issue being the safety.
Okay. That's a good question. I'm not sure I'm the right person to answer it. I wonder if someone here is better able to answer that than me. Just sort of my impressions are that, in North Carolina, for example, some of the trucking interests are fairly politically powerful, and just from my perspective, it seems easy to get exceptions for heavy load trucks to operate on the road. And I actually live near a sort of a truck, a dump truck depot, and the road that those trucks drive on is of different quality than the other roads in the area. So, there is some effect on the roads. But yeah, I guess in terms of truck sizes and so on, I don't know, I guess the trick would be how do you incentivize that? I'm not really sure. In a European city where there's a lot of congestion and not a lot of space, trucks I think are smaller than they are here, but we have more open space, and I guess all else being equal, it's probably more fuel efficient to have the bigger truck than the smaller one. So I don't have a magic bullet to solve that one.
Any other questions from the room?
Yes, I enjoyed your talk. My name is Steve Prey. I'm the Energy Conservation Program Manager for Caltrans. In your numbers and review on diesel vehicles, have you looked at heating the fuel prior to combustion, which will take the paraffin out of the equation as a soot generator and turn it into a BTU additive to the fuel per gallon and therefore solve a whole bunch of problems?
Yeah, we haven't looked at that, so that might be something else we should add.
Because we're looking at 12 to 18% increase in BTUs per gallon.
Mm-hmm.
And at the same time, it drastically reduces the soot output if, for all intents and purposes, eliminates it.
Mm-hmm.
Because most of that carbon output is unburned paraffin. And if you're looking at biofuels, you know, you're still got a diesel component, so you'll have a certain percentage ratio depending upon whatever you're using as a substitute. But it's one of those areas that needs to be included in the calculations because it drastically changes a lot of the pollution issues. In fact, we've got a couple vendors here in California that have passive devices that are also looking at generating active devices that would be applied to the older engines. Hopefully the newer trucks and cars that are using diesel are coming out with fuel preheaters. But all you have to do is get the fuel up to about 150 degree Fahrenheit and you're sitting pretty.
Okay. Well, yeah, I'd be interested in finding out more about that.
Okay, we'll do one more from the webcast.
Okay.
The comment is, what happens to the study now? What are the practical effects of the guide in terms of real-world applications? So in other words, they want to know, is Volvo going to implement some of the best practices, or where do we go from here with your findings?
Oh, I'm sorry, I missed one word. Who implementing?
Volvo?
Oh, Volvo. Well, I guess there's several separate components to that question. So the guidebook is more or less, you know, a final product of a specific project, and so it's, you know, what I've recommended are some things that I think would be good next steps, but for them to happen, there needs to be resources to do that. So I guess I'm interested in exploring that if anyone here is interested in supporting some of those recommendations to take that forward. But I think the guidebook itself, the intent was to, you know, try to have kind of one place to disseminate in some amount of detail information on a variety of best practices and just make them more widely known among the freight community. And, you know, the intended audience for that is fleet owners, it's government agencies, you know, basically anyone who might have some role in making decisions about adopting potential best practices. So we've only recently been able to release that report because it underwent, you know, a number of review stages with USDOT, and which improved the report. So I guess I don't know quite yet. The answer is, you know, what's the effect? I guess I'm looking for feedback on that as people use it. And then the issue with Volvo is that's kind of a separate project that I mentioned just as an example of where you can get into much more detail in any specific best practice. And so, I mean, one thing that Volvo has done is they have developed what they call a prep kit, which is to basically pre-drill all the holes and, you know, facilitate the installation of an APU if a customer wants to buy an APU. So if you buy a Volvo truck, you can specify as an option the preparation kit for an APU, and that becomes part of the truck that's delivered to you. And then you would probably typically arrange to have the APU installed by a third party. But it's much easier to install the APU if you do a few preparation steps than if a third party has to drill holes in the frame rail and things like that, which gets into some more serious labor hours and so on. So I mean, that's one thing that they're doing, and they're obviously as interested as we are in the results of this study. So you know, we're still not quite finished with the study yet. So I think we'll see.
Any other questions from the room? Chris, on behalf
All
of
right.
the Air Resources Board, we want to thank you for coming and sharing lots of good information. I'm
Yeah.
sure a lot of us are going to be in
Thank you.
contact with you.